All right, good afternoon, everyone. We are Status Airway. My name is Joe Saldana. I'm the project manager for the hardware team of Status Airway. Thank you everyone for coming today. Whether you realize it or not, San Diego Gas and Electric had a big part of you being here today. Whether it was charging your phone last night so your alarm clock would go off this morning, or you have an automatic coffee maker that has your coffee ready for you in the morning. If you have an electric car, you probably wouldn't be here right now if your power went out last night. So SDG&E is continually trying to improve the reliability of their distribution systems. In 1998, the average customer saw one outage every year, and that outage lasted for about 90 minutes. Today, that number has gone down to one outage every other year, and it only lasts for about 60 minutes. This is why they've been voted best in the West in reliability for the past 10 straight years. Some of the things they've been doing to get that honor is using more renewable energy, smart grid technology, increasing the amount of automation they have on their distribution systems, and using the technology that we're most concerned with, the wireless fault indicator, shown in that picture there. So what this device can do is it can measure voltage and current real time. It sends this data back to an online database during an outage or during normal day-to-day operations. And an operator can use this information to real time just establish where the issue was that might have caused the outage. So right now, the WFIs are installed using a bucket truck, parked at the bottom of the pole, install it up on the line using a hot stick. So the problem is that there are many places where there's environmental issues, low access issues, and WFIs aren't able to be placed everywhere that SDG&E wants. So that's where they came up with the idea to use unmanned aerial vehicles, UAVs, or drones to set these. Now, drones are being increasingly used in all different types of industries: customer package delivery, medical supply delivery, farming, emergency response, and yeah, you guessed it, electric utilities. So last summer, SDG&E was approved by the FAA to use drones in their day-to-day operations, and since then, they've been using them to inspect transmission lines, distribution lines, any facilities that have low access issues. And it's this fact, it's the success of the drones that have come to us to task us with the challenge of using a drone to set these WFIs. So at the beginning of the semester, we set out some goals. We wanted to create a system that functions safely and reliably. Our first goal was to build a device that mounts on top of the UAV. This goes back to the first priority, safety. If the drone is operating below the distribution line, any type of malfunction, unseen weather condition, operator error, the probability of the drone colliding with the line is much less if it's operating below rather than above. And so we also are utilizing sensors to detect the line. Because of the top-mounted mount, we needed to modify some of the weight so that we'd have a lower center of mass and keep a stable flight. And lastly, we're going to document the entire process so that this can be realistically done in the field. I'm going to bring up Clint, and he's going to talk to you about a high-level version of the process.
Great, thanks, Joe. So good afternoon, everyone. I'm just going to run through an overview animation of what our system will do. And before I do that, I just want to let you know that we have two flight modes. The one is autonomous, meaning it'll use our sensors that we'll use to fly and get the drone up into the line, and then finally it'll operate manually with a SDG&E lineman, where he'll fly the drone into the line and attach the WFI. And before takeoff, the lineman will input a value of the height of the line from the ground to the drone, or from the ground to the line, and the drone will ascend until it reaches about that height. And then as it approaches the line, the next set of sensors will detect the line, and then it'll also adjust the orientation or the vehicle yaw of the UAV. And as you can see here, the UAV will be about 30 degrees away from being parallel or being perpendicular with the line. So our sensors will detect that and adjust the yaw so that it is directly towards the line. And then finally, the last set of sensors we'll use is to detect the distance and modify the height of the UAV to the line, and it'll oscillate back and forth as you see here, just so that the payload is directly where the lineman wants it to be. And after that, we'll finally switch into the manual mode, which will give us a view from the cameras, which is directly straight at the line and underneath the line, where the lineman will use those to fly the UAV into the line right there. And for all of these components, We're just going to discuss that even more, and I'm going to bring up Kim for that.
Thank you, Clay. As you see in the 3D animation, the housing and latch release mechanism have a sensor system in there to detect the wire and to orient the vehicle. And the sensors are LiDAR and ultrasonic. Now I will talk about the LiDAR. LiDAR stands for light detection and ranging. It's a remote sensing method that use light as a pulse laser to measure range and variable distance. For our project, we choose the LiDAR Live version 2 to work with. That model have the maximum range is 40 meters under typical condition, and its accuracy is 2.5 centimeters. The other features that make us to choose this version to work with is because it has a really lightweight, about 22 grams, which is not too heavy to put on the drone. And then it has the I2C and PWM interface to process the signal. For our project, we use total 2 LiDARs. We use 2 LiDARs for 2 different purposes, but they both operate in PWM interface to processing the measurement. One LiDAR is facing forward to detect the wire and the distance between the wire and the UAV within 5 meters. And the other one is facing downward to keep track of the altitude. And the facing downward LiDAR come to replace the barometer, which is originally come with the drone. And the barometers use barometric pressure to determine the altitude of the drone, but we found that it's not accurate because the measurement is fluctuate a lot. So compared to the LiDAR, the measurement from the LiDAR is more stable and more accurate than the one come from the barometer. Next, I'll pass to Maya. He will talk about the ultrasonic.
So from the animation, we're using 2 ultrasonics. And the ultrasonics, we ask ourselves, like, what is it? So an ultrasonic will send a signal to an object and bring it back, and it determines the distance based on the time it takes for that signal to get there. I practiced with the LV Max Sonar Easy sensor first, and it has a max range of 600 centimeters. But the problem with it is that it has noise interference. So thankfully, Maxbotics, the manufacturer for ultrasonics, was able to provide an XL Max Sonar WR series. This one also produces 600 centimeters, but there's less noise interference, which is why this is specifically for UAVs. We're sticking with a 3.3 volts instead of a 5 volts that the ultrasonic can also produce, and it's fine. And with the 5 volts, it's 700 centimeters, but in this way, it's fine. The weight is 50 grams, much heavier than the LV Max Sonar, but the efficiency, I believe, will be more important later on. The pins that the ultrasonic uses is PWM, transmitter, receiver, and the analog voltage. I decided to use the analog voltage because it's much easier to use, and especially when we're working with 2 sensors, the ultrasonics with the 2 sensors will be able to detect everything based on the voltage, because that is the range in the centimeters as given by the manufacturer. And I tested this from the lab via multimeters and debugger, and it was able to detect the wire from that. So now I'm going to take it over to Joe, who's going to talk about the camera.
Yeah, so the final step in the process, and the only manual part of the process, is the cameras and the screens here. So we bought lightweight cameras. They've been shown to do well for drone applications before, and we oriented them in a way on the drone so that this is the visual they can see. As soon as the operator sees that the conductor go across the horizontal of the 2 screens, he knows he's in the right position to run it into the line and have that WFI snap into place. All these sensors, cameras, it's all connected through the WFI housing, which Clint is going to go over.
So here's just another mock-up of the housing that we made. You can see the ultrasonics and all the components that we've already talked about. And the next question you might ask is, how are we going to connect the WFI to the line? And we're actually going to use these other components right here. So we have the latch bars, and they're there to hold the clamp back to leave it open for the wire to hit. And then we also have the servo motor, which will control those latch bars, which are on a linear bearing system, which will actuate those bars and move them out of the way. And then we also use a piezoelectric sensor that will trigger the servo motor to move and release the bars. And the system that we're going to use for the piezoelectric sensor will be a system where we'll arm it once the cameras are set and the operator's in manual mode. So the interference from any vibration from the flight going up will not be detected and not trigger the release. Here's just another animation of how that will work. And just to clarify before I go through the animation, just the line that we're going to use is de-energized, so there's not going to be any current going through it, and all of the other effects from that won't be part of our project. So we'll see the line hit the housing, and as it hits the housing, it'll send a vibration through the piezoelectric sensor. And what the piezoelectric sensor does, it transduces the physical vibration into a voltage, and that voltage will go to our microcontroller, and our microcontroller will then trigger our servo motor to move from the lock position into the open position. And as it opens, you can see the latch bars move sideways, and that will release the bars and clamp it onto the line. And here you can see a mock-up test in the lab of it just releasing, and also a picture of our mounted payload delivery system on the UAV. And for all of these components that we use, the data is going to be sent into our microcontroller, and then Matt's going to talk about that more.
So the microcontroller we decided to use is the PIC24. The reason for this is because it has the analog digital converter we need, but also because it has 5 pins dedicated to the pulse width modulation that will be used for the LiDARs and the servo and the piezo. The other most important thing about this is that we needed to have the I2C for the support serial communication to get all the data that we get from the microcontroller down to the ground station. To debug, we stuck with the MicroStick 2. This is very versatile and easy to use. And as you can see here, these are the pins that are specifically for each of the things that we're using. And to talk about the process of the PIC-SOC, I'm going to send it to Ariane.
Thank you, Mayok. To start off the software description, I'll first introduce what a PIC-SOC is. And it's very light. It's a device that you can hold in your hand, and it weighs about 38 grams. And it's basically very crucial to the project because it acts as the brain of the drone. And it features a microprocessor of 32-bit Cortex-M4 core with a 32-bit fail-safe coprocessor. And it also features built-in sensors, which is the gyroscope, the accelerometer, and the barometer. And it has a built-in advanced autopilot system with the APM flight navigation software, which the software team modifies so that it would work with our sensors and the serial communication, and to get the drone to fly autonomously. And the ports we use there's 3 key ones. One is the aux out here, which is connected to the LiDAR that's facing downward for altitude, and the telemetry 1 port, which is the radio down to ground station, and the I2C here, which I will pass off to Andrew to go into more detail about.
So we had to choose between 3 different kinds of communication to overcome the ports that we had before, that you saw before in the previous slide. There's a limited amount of ports, so we can only choose between 3 different modes of communication for the PIC and the PIC-SOC to communicate. We chose I2C for its accuracy, speed, and flexibility. It is a master-slave system, the PIC-SOC acting as the master and the PIC acting as the slave. And we only needed 2 wires to communicate between the 2 of them, which made it very simple to implement, a clock and a data line. And so every time the clock falls, it gets the data off the data line. That makes it very accurate, so you know exactly what's being sent every single time. Now, to get an idea of the speed of the system, the communication refreshes between the 2 about every 10 milliseconds, which is pretty fast, and that's more than what we need for our uses. It also uses a 100 kilohertz bus and 7-bit addressing, as opposed to the 10-bit addressing system. The PIC-SOC only supports 7-bit addressing. That means that everything that we're communicating here is only going to be in 8-bit packets. So everything, we're going to have 4 values sent between these 2 things, and every single one of them is going to be in 8 bits. That limits us to values between 0 and 255. So the units for these sensors that the PIC-SOC will be taking in will be in centimeters. So that gives us about 8 feet. So that means that the drone's going to have to be placed within 8 feet of the line when it's coming up. But we don't foresee that as a problem. We think that that would be all right for the user to use. And so, as I said, 4 values, and then each one is from sensor, 2 from the ultrasonics, 1 from the LiDAR, and the last one is status flags. So we'll have 1 value with each bit being a status flag. That'll tell us if something is failing or if we have a problem with the latch or something's not right, or to arm the latch and when the latch is fired and then the mission is complete. And to talk about what we're going to do with those values, I'm going to bring up Justin to talk about the autopilot system.
Thank you, Andrew. So I'm here to talk about our state machine we created for our autopilot flight. The initial state is a launch state in which the user will specify an altitude, and once that altitude has been specified and the mission begins, the drone will rise to that altitude. This altitude should be slightly below the wire. Once that altitude has been reached, we continue to the next state in which the drone will ascend by setting its target climb rate positive, and it will rise until the ultrasonic sensors detect the wire. Once the ultrasonic sensors have detected the wire, we're going to lower the climb rate, we're going to adjust the orientation as seen in the animation. So if the drone is not facing the wire directly, we're going to adjust the yaw so that, based on the ultrasonic values, will be centered correctly. Following that, we're going to set the target climb rate again to increase altitude until the LiDAR detects the wire. If for some reason, while the drone is ascending, we don't read the value of seeing the wire, we'll go into this state which the drone will descend, because we know since we're ascending, we lost ultrasonic detection, we're above the wire. So we have to descend until ultrasonic detect again, and the reverse happens. And then we'll check for LiDAR detection again, and once that's been re-achieved at either state, we go into the next one, in which we'll send an alert to the user saying that the drone is in an acceptable position to be manually flown into the wire. At this point, we'll be in an altitude hold mode where the drone will hold its position until the user takes manual control. When the user arms the drone with manual control, he will fly the WFI into the wire, and once the piezo releases the latch of the WFI, it will hang onto the wire, and that will push it to the last state in which the drone will just return to launch. To talk about how all this data is displayed to the user in our ground station, I'm going to bring up Lance.
Thank you, Justin. So this is a view of what it looks like, our system on the ground. I'm going to be going into a little bit more detail of what you can see here in the tablet. It's an application called Mission Planner that we used in our system as the ground control for our system. Mission Planners, we picked Mission Planner for a lot of reasons. One, it's an open source code, so we can get the code for free and modify it as much as we want. It also has a very large support community, so we could reach out on forums anytime we got stuck. Third reason being that it's written primarily in C# programming language, which all of our team felt pretty proficient in going into this project. The functions of Mission Planner are primarily to set up new flight plans, to watch real-time telemetry data come down from your flight, also to go back and view logs from previous flights. As we wanted to make our flight mode as autonomous as possible, this is what the pilot's mostly going to be interacting with, and not so much the UAV itself. I'll show you guys exactly how it looks. When you open up the application, the pilot's going to be presented with this quick pre-flight checklist. If he responds correctly to all these pre-flight checklist questions, the actual application that you can see here, Mission Planner, is going to open. This is where he's going to see all the telemetry being brought down from the flight. This is also where he's going to put in the initial waypoint to set the altitude of where the UAV should go up to. All these telemetry data are being brought down from the Pixhawk over what's called MAVLink, Micro Aerial Vehicle Link. It allows for the ground control station to send data up to the Pixhawk, as well as request new data to be sent back down. Data packets are accompanied by header information as well as error detection information into messages that can reliably be sent between the two systems. This is how we're going to get our ultrasonic data and our LiDAR data, as well as all the other data that we need in the flight to be sent down to ground control, so that the pilot can look at and watch all this as it changes real time. To make all this more user-friendly, we made a UI you can access by clicking the button up top. This brings up a very user-friendly view of what the UAV is doing in respect to the wire. The rotational position in respect to the wire can be seen up here, the difference between the ultrasonics as well as in the picture, and then the track bar across the bottom. These all tell the user what the UAV is doing in the air, in position, rotational position in respect to the wire. Also gives you a real-time update of the LiDAR, downward-facing LiDAR for altitude, as well as the forward-facing LiDAR is represented by that red circle in this slide. That basically says that the forward-facing LiDAR at this moment does not see the wire. When it does, that circle will turn green, and indicating that the forward-facing LiDAR does see it. When that turns green, the difference between the ultrasonic goes to 0. He will get a status message saying that it's time for him to arm the UAV and fly it into the wire. At that point, he will fly it into the wire, and the UAV will successfully complete the mission and return to launch. Now to talk about power management, I'm going to bring up Alex.
Thanks, Lance. Hi, everyone. My name is Alex Arways, and I tasked for power management here. So obviously the big challenge is the weight distribution. Want to be able to maintain and have successful flights. So we migrated from a 6 ampere battery to a 10 amp battery. And I know this is a lot of information, but this is kind of a dashboard that I created to kind of get a good sense of flight times and things to consider. So this is basically a repository of information from the drone and also some of our captured flight times. So some of the things that I considered obviously is just the general information here. It's an 8-rotor UAV, the battery cell, the electronic speed controls and motors and the propellers, the size of the propellers. And these gauges are just a representation of the tolerances. And obviously, as you can see, the drone is pretty close to the red areas. But and down below here is just a derivation of the battery and how it performs. We were able to get a successful 6-minute flight time given the load. And also we're able to gauge the motor optimum efficiency, the motor maximum, and the motor at hover as well. So just to kind of consolidate this a little bit, the overall, again, flight time and the goal is we were able to achieve at least 6 minutes considering the weights and again, given the battery capacity here. Next, again, just the whole point of that dashboard is obviously kind of a safety measure so that we make sure that we didn't burn up our motors or anything like that. So after this regression analysis, obviously, after we all felt good about the stock motors, staying on board, we knew that every motor can handle at least 27 amps. So it wasn't too hot. It flew really well, and we were able to get 6 minutes of flight time. I'll transition to the budget here. As you can see, our expenditures were pretty conservative. Cost savings was close to 60%. I think obviously the hardware was the video components were pretty much the most expensive things out of the budget. But given the $3,500 budget that we were given, we were still able to be conservative and stay within our realms. So I'll pass it off to Joe. He's going to discuss the achievements.
Yeah, so the first major achievement was the weight distribution, which I was talking about earlier. After initial flight testing, so you can see here the battery is right underneath the body with the Pixhawk here right above it. We set the WFI above that, and we did some testing. I'm not going to show you that testing. You can see that after if you want to. But after some movement of weight, which is shown right here, we built a platform for the battery to drop down. We also moved the Pixhawk down to right here underneath the body, and that way that gave us the ability to move the WFI all the way just on top of the body of the drone. So it drastically moved the center of mass lower, so we get a more stable flight. So this is just in the air, hovering about 10 feet, and you can see it's pretty stable. I'm not really moving the controls much, so much more stable flight with the movement of the weight. The other thing that we achieved as well was the ultrasonic and LiDAR sensors communicating through a PCB that we designed and built to the microcontroller. Also the I2C between the microcontroller and the Pixhawk. Andrew talked about how fast, how accurate, how flexible the I2C can be over other systems, but he didn't really talk about how complex it is. So it was a really big accomplishment for us to get that communication working. Also, as Lance was talking, the MAV link between the PICSOC and the ground station was a big thing for us. And finally, the operation of the WFI housing, as you saw with Clint's video of the latch being able to snap down with the sensor. We created this long line of communication between all these devices. We were unfortunately unable to test it with making that final step from PICSOC to movement of the motors and doing it, making the motors move like we wanted them to. We did learn a lot of other things, such as the planning, the teamwork, the project management that goes into a challenge like this. We learned technical skills using software to build the PCBs, the animations that you saw, all the different coding that goes into the sensors that we were using, and also soft skills, coordinating a useful team meeting and managing the resources that we had to complete the project. For that, those skills could be used in our future engineering careers, and we're grateful to Professor Kennedy, Dr. Tamala, and our sponsors and mentors from SDG&E. We hope you guys can come out to Design Day, where you can see those successful portions of our project more up close and personal. Thank you, guys.